So as we talked about previously, you can only do L'Hopital's rule if you have 0 over 0 or infinity and infinity. So make sure just because you have a fraction doesn't mean that L'Hopital's rule applies. So if you look at this problem here, if I plug in 0, notice I will have 2 on the top, 1 plus 1, on the bottom you have 0. This is not an indeterminate form. Indeterminate form is 0 over 0, infinity over infinity. Okay. 2 divided by 0. Remember, this is a limit problem. So the top is 2, you're approaching 2. The bottom, you're approaching 0. It's saying the bottom is getting smaller and smaller. So when you are doing a limit problem and you have a number on the top and 0 on the bottom, really your limit is infinity because the bottom of the fraction is getting smaller and smaller, so the entire fraction gets bigger and bigger. So there's no need to use L'Hopital's rule here. Okay, there's two other indeterminate forms that we're going to talk about. The first one is when you have 0 times infinity. Again, these are all limit problems, so it's not that the number itself is actually 0, you're approaching 0. So 0 times infinity is not necessarily 0, it's not necessarily infinity, it may be or may not. It may be something else. So first thing, check if you get to this indeterminate form. So if I plug in 0, notice I get 0 times natural log of 0. Think about your log graph. This is your log graph. This is 1. As you approach 0 from the right-hand side, notice the log graph is going to negative infinity. So this could be 0 times infinity or negative infinity. So this is really 0 times negative infinity, which is an indeterminate form. Now you cannot use L'Hopital's rule here. You can only do L'Hopital's if you have 0 over 0 or infinity over infinity. But I still don't know what this limit is. But the idea is I want to be able to use L'Hopital's rule. So I'm going to rewrite this problem as a fraction. Now you have two choices. You can either write it like this, right? This is the same problem if I flip that fraction, or you could write it like this. You could leave the x squared on the top and then put this piece on the bottom. Right? This is just another way to rewrite this original problem. What you want to do is rewrite it so it's easy to take the derivative of the top and the bottom separately. I would say this is easier for me to take the derivative of the top and the bottom separately because this piece here, you've got a little bit of chain rule going on when I take the derivative. So I'm going to go ahead and rewrite it like this. Now let's see what happens when I plug in 0. If I plug in 0, remember we just said the natural log of 0 from the right-hand side, this is negative infinity. On the bottom, 1 divided by 0. Again, the bottom of the fraction is getting smaller and smaller, so the whole fraction gets bigger and bigger. So really in this problem, you have infinity over infinity again. So now I can use L'Hopital's rule. So the derivative of the top will be 1 over x. The derivative of the bottom is just x to the negative 2, so bring down the power, reduce the power by 1, and before I start plugging in my 0 again, I'm going to simplify this a little bit. So this will, if I flip the fraction, simplify to x squared on the top, negative 2, and now if I plug in 0, you just have 0 divided by negative 2, which is 0. Okay, let's get the second one. Okay, start by plugging in the value. If I plug in pi halves here, I get pi minus pi, which is 0. Secant at pi halves, if you think about your secant graph, you have an asymptote at pi halves, it's actually infinity. So again, you have this form 0 times infinity, which we don't know what that is. So again, I want to use L'Hopital's rule. The only way I can use L'Hopital's rule is if I have a fraction. So I'm going to rewrite this as a fraction. And I would say this is the easiest rewrite. Put that secant as 1 over secant on the bottom like this, because what happens is then the bottom is really just becomes cosine. So now if I plug in pi half, I do have 0 over 0, so I can do L'Hopital's rule, which says to just take the derivative of the top and the bottom separately. Derivative of the top is 2. Derivative of the bottom is negative sine of x. Now if I plug in pi halves, this is 2 over negative 1, and my limit is negative 2. Okay, one last indeterminate form. Sometimes you may end up with infinity minus infinity. Again, infinity minus infinity is indeterminate because it's not necessarily 0. It's not the same value. Okay? So here, if I plug in 0, you have 1 divided by 0, which is infinity. You have 1 divided by 0, which is infinity as well. So there's our indeterminate form. But again, I want to use L'Hopital's rule. The only way you can do that is if you have a fraction. So if you have two fractions just being added or subtracted, just make it into one fraction. So I'm going to rewrite it by getting myself a common denominator. So I need an x on the top. I need that e to the x minus 1 on the second piece. So now I have rewritten the problem with the common denominator. It's one fraction. So let's check. If I plug in 0 at this point, you will get 0 here, 1 minus 1, so I have 0 on the top. I have 0 times anything is 0. So I do have 0 over 0. So now I can do L'Hopital's rule. The root of the top is 1 minus e to the x. The root of the bottom is, you can either multiply it out or use the product rule. I'm going to use the product rule. The root of the first is 1 times the second plus the root of the second is e to the x times the first. Okay, now let's plug in the 0 and see what happens. If I plug in 0, I get 0 on the top. If I plug in 0 here, this is 1 minus 1, which is 0, plus another 0, so I have 0 over 0 again. So I'm going to do L'Hopital rule one more time. Root of the top is negative e to the x. Root of the bottom is e to the x. This becomes 0. Product rule here. Root of the first times the second plus root of the second is 1 times the first. And let's see what happens if I plug in 0. I have a negative 1 on the top. This is 1. This becomes 0. This is 1. So there's my limit.